In 2020, a healthcare SaaS company's patient scheduling system double-booked a clinic slot. The engineering team's first response was confusion. The system ran on PostgreSQL. PostgreSQL is ACID compliant. ACID guarantees consistency. The slot should not have been bookable twice. What they found, after several hours of investigation, was that their connection pool was operating at read committed, PostgreSQL's default isolation level. The scheduling process read an availability slot, performed a calculation, and read the slot again. Between those two reads, a second transaction had modified it. The process had seen two different values for the same record within a single operation. The ACID guarantee was real. It just did not cover what the team had assumed it covered. The database had delivered exactly what it promised. The team had assumed it promised something more. Consistency guarantees are not single properties. They are layered, scoped, and conditional. A database advertising ACID compliance is making specific promises about what happens within a transaction. Those promises apply at a specific isolation level, under specific conditions, within a defined scope. The headline, ACID, strongly consistent, durable, describes a capability. The actual guarantee depends on how that capability is configured and under what conditions it holds. Most production failures that trace back to consistency do not happen because the guarantee was broken. They happen because the guarantee was narrower than the assumption. Three specific gaps account for most of them. The first is isolation level assumptions. Isolation levels determine what a transaction can and cannot see from concurrent transactions. Read committed, the default in PostgreSQL, Oracle, and SQL Server, guarantees that a transaction will not see uncommitted data. It does not guarantee that two reads of the same row within the same transaction return the same value. At read committed, they can differ. At repeatable read, they cannot. At serializable, concurrent transactions behave as if they ran sequentially. Engineers who assume their transactions are fully isolated are often assuming repeatable read or serializable behavior from a database running at read committed. If the isolation level was never set explicitly, the default is the one you have, and the default is rarely the strongest option. The second is replica scope. Most database consistency guarantees apply to the primary node. When reads are routed to replicas for load balancing, geographic distribution, or cost, the consistency properties change. Asynchronous replicas lag behind the primary. A read from a replica may not reflect a write that completed moments ago. The ACID guarantee lives on the primary. The replica does not carry the same promise. Engineers who understand this at the architectural level often forget it at the operational level. In systems where replica routing is handled by an ORM or a connection pool, the routing is invisible in the application code. Nothing in a query signals which node it is hitting. The third is configuration drift. Many databases ship with defaults that are safe for general use, but weaker than what critical operations require. Isolation level defaults, synchronous commit settings, consistency levels in distributed systems. These are set once and rarely reviewed. Infrastructure updates and library upgrades can change them silently. A system that behaved consistently under one configuration continues to operate without error under a weaker one. No alert fires. The guarantee quietly narrows. The next time an operation depends on a property that the configuration no longer delivers, it fails, and the failure looks like unexpected behavior rather than a configuration problem. Three things address this. The first is verifying guarantees at the operation level. For every operation where the result is used to make a decision, check what guarantee it actually has, not the database headline. The isolation level that is active, whether the read hits a primary or a replica, whether the operation runs inside a transaction and what that transaction covers. This is not a one-time audit. It is part of the design process for any operation that touches data your system relies on to be correct. The second is making isolation levels explicit in code. Do not rely on database defaults for operations that require consistency. Set the isolation level explicitly in the transaction that performs the operation. If a scheduling process reads a slot and then writes to it, and the slot must not change between those two steps. Repeatable read or serializable is required. Write that requirement in the code alongside the transaction. When the isolation level is visible in the code, it can be reviewed, tested, and maintained. When it is inherited from a default, it is invisible until it causes a failure. The third is assumption documentation. For each critical operation in your system, record what consistency property it depends on, not in a separate document, but at the point in the code where the operation runs. A comment, a transaction annotation, a test that validates the property holds under concurrent load. This converts an implicit assumption into an explicit contract. When infrastructure changes, a new replica, an ORM upgrade, a configuration update, the documented assumption is the thing you check against. Without it, configuration drift is invisible until the data is wrong. The healthcare team fixed the immediate problem by setting the scheduling transaction to repeatable read. They then audited every critical transaction in the system, documented the isolation level each one required, and made it explicit in the transaction definition. The double booking had not been caused by a database bug. It had been caused by an assumption that was never verified against the actual configuration. The database can be ACID compliant and still return inconsistent results within the same operation. The guarantee applies only when the conditions for it are met. The gap between what a system can guarantee and what an engineer assumes it guarantees is not a documentation problem. It is an operational one. The guarantee is written down somewhere. The assumption is not. Closing that gap requires making the assumption exactly as explicit as the guarantee it depends on.